Hey, this is Mr. P, and today we're going to be thinking about measurement, sig figs, averaging, and accuracy versus precision. So basically, in physics, when you write a number or a measurement, it can actually communicate multiple different things. So the first thing, which is the thing that you're already familiar with, is the magnitude. So magnitude is basically the size. So obviously 45 meters has a larger size. If you're just thinking about magnitude, you can use absolute value symbols. Then let's say 30 meters, since 45 meters is longer than 30 meters. But the tricky thing is that magnitude is not the only thing that we can communicate with numbers. So another thing that you can communicate with numbers is direction. So for example, you might have seen in your math class that you could write a vector like 10 meters, 45 meters, where the first part is saying how far you're going to the right, and the second part is saying how far you're going up. In physics, we're generally going to write the direction in words. So if this quantity had a direction, we might say 45 meters to the left. Right now, we're not going to focus on direction, but that's going to be important later on. And the last part of the thing that we can communicate with numbers is what range of values the measurement represents. So the important idea is that in this class, if you write 45 meters, that doesn't mean that we're communicating that the value or magnitude of this is exactly 45 meters. We're just saying that it's something close to 45 meters, and that's sort of what we're going to be thinking about in the rest of this screencast. So before we go any farther, let's see if you're paying attention. What does the word magnitude mean? Every student in this class is going to have a choice to make, which is to either build good habits with units, or you can choose to lose points. We are going to look for and grade units on essentially every quiz and test and lab in this class, and if you're making mistakes with units, they're going to just continually add up over and over and over again. One thing that students ask me often, and it's a good question, is they say, Mr. Flommer, I just get overwhelmed. How am I supposed to pay attention to all these units? And the answer is, if you have not already built up a good habit, it's already too late by the time of the quiz or the test, because you're going to be thinking about the specific question that's asked and you're going to forget about the unit. On the other hand, if you build good units and you just practice every single time you write a number, you put the unit and you just get that habit, you're going to write the units without even thinking about it because you built a good habit. So choose wisely if you're going to build those good habits or not, but realize if you don't, it's something that's going to come up time and time again in this class. So I really hope that you do choose wisely. Suppose you had a multi-million-dollar lab with 100 professional physicists. Could you perfectly measure the length of the table? I would argue that you can't. There's two basic problems. So first, you're going to use some kind of measuring tool to take the measurement. So let's say we use a big tape measure that looks like this, and there's markings on the tape measure for every meter. Then it's pretty clear in this case that the table is between 2 and 3 meters long. But there are no markings on this tape measure between 2 and 3 to know if it's 2.4 or 2.5 meters. So how would you tell? And even if you got another tape measure that was more precise and had more digits in between the 2 and the 3, fundamentally we still have the same problem. There's going to be a point where we can't tell between this place and the next notch. And there's no way for us to have an infinite number of notches. So it's always going to end up between two notches, and we won't be sure how far in between it is. So the tool itself limits our ability to be certain about the measurement. The second is our ability to use the tool. Imagine that we had a tape measure over here that had tick marks every nanometer, so that's really close together. That's great, but the problem is that we wouldn't be able to read those tick marks. They'd be too close together. So if we can't read the tick marks, we still don't know if it's between one tick mark and the next, and therefore it's still uncertain. So either one of these things, the tool itself or our ability to use the tool, can limit the ability to get a perfect measurement. We cannot ever do that in physics. Let's say you're planning a party and you say that 20 people are coming. Most likely you don't mean that exactly 20 people are coming. Maybe it's somewhere between 18 to 22, or maybe it's between 10 to 30. Now, as the party planner, it makes a big difference to you if the range is between 18 to 22 or if it's between 10 to 30. what we're going to do in this class is we're going to figure out what we know and what we don't know about the measurement, and then we're going to communicate that to other scientists so that they know what is known and what is a guess. The procedure that we're going to do for this is always the same no matter what the measuring device is, and it's something we're going to use over and over and over in this class, so you got to know how this works. So the basic idea, let's say we look at this protractor and we're trying to find the red angle here. First, you figure out what you know for sure, and this is something that 100 physicists measuring it 100 times, they're all going to agree because there is no doubt. So make sure you know what the tick marks are. In this case, it goes 30, 40, 50, 60, so each tick mark is 10. We can say it's definitely between the 40 and the 50, but there are no tick marks in the ones place, so we don't know if it's 43 or if it's 44 or whatever. So once you get to a digit that you don't know, you make one guess and you stop there. So the correct measurement here is 44 degrees. Now you could have said 43 degrees, because remember that the last digit is an estimated one anyways. So we're not saying that in either one of these measurements, we're not saying it's exactly 43, we're not saying it's exactly 44. Usually you use about plus or minus 1 or 2 in the estimated digit. We're saying it's something close to that, but it doesn't have to be exactly 44 degrees because we simply can't tell that. So a key point here is to just write down what you know and make one guess and go no farther. If you think about this protractor example, I would argue that it doesn't make any sense to say 44.43147 degrees, because we already don't know the ones place. And if we don't know the ones place, what sense is there in putting a bunch of other random digits that we don't even know, so they're just wild guesses? The other thing that's bad about this is that if you write down 44.43147, and let's suppose another scientist looks at this and they are following the same convention that you are, they are going to say, well, since you wrote down all these digits, you must know all these digits. And they'll say, I think that you're making a guess about this last 7, but you know the rest. The problem is that you don't. There wasn't even markings on the protractor, so you are claiming way more certainty than you actually know. Okay, so please use the procedure to figure out how much water is there in the cylinder and explain your reasoning. Let's practice measuring one more time. So please find some object and some kind of measuring tool. It could be a protractor, ruler. You could get like from cooking, something like graduated cylinder or something. Find an object and measure its length or height or angle. I don't really care about that. Remember that the important thing about this is the certainty of the measurement. Let's think about a tricky case. What if the measurement ends in 0? So if we look at the top meter stick, you can see that the blue bar is about 20 centimeters long. And if we look at the blue bar measured by meter stick B, it also looks like it's about 20 centimeters long. You can see that both of these bars are a meter long, and this one has a marking halfway and this one has markings every 10 centimeters. When you look at those two measurements, obviously with this top meter stick, which has more markings on it, which we can clearly read, we know that measurement with more certainty than we do for the bottom one. And so we need some way to communicate that. And it gets tricky to tell where is the known and where are the estimated digits when the digits end in 0. And so because of that, we have these set of rules